Hello and welcome to Chapter 13. We are going to look at gas laws in this chapter. And for the part 1 video, we're going to look at three basic gas laws. The first law we're going to look at is Boyle's law. Now, Boyle was an Irish chemist, and what he was concerned with is he was looking at how pressure and volume in a system were related. So the thing that you have to remember with Boyle's law is that he kept temperature at a constant rate, as you can see here, and the amount of gas was constant. So we weren't changing the quantity, but what he noticed based on one of his experiments was that if you doubled the pressure, then the volume would decrease by half. So he concluded that reducing pressure by a half would increase the volume by doubling. So it's an inverse relationship then. If one is going to increase, the other is going to decrease. Okay, and you can kind of see that mathematically on the curve right here. So as our pressure starts to increase, you can see that volume decreases. Likewise, if pressure decreases or goes in this direction, then our volume increases. Okay, again, and we call this inversely proportional. So if you look at the true definition of Boyle's law, it says it's the volume of a fixed amount of gas held at a constant temperature, and the volume is going to vary inversely with pressure. So the formula that we're going to have to look at is P1V1 equals P2V2. Now the 1 and 2 just kind of represent maybe like an initial for 1 and a final for 2. That's probably the easiest way to memorize it. P represents pressure, V represents volume. Okay, and what I'm going to suggest is the three laws that we go over today, you should have a general idea about them, but we're going to use something later on called a combined gas law, and I think that formula is best to memorize instead of each of these three individually. So let's go ahead and look at how Boyle's law can be applied. It says a diver blows a 0.75 liter air bubble 10 meters below the water. As the bubbles rise to the surface, the pressure goes from 2.25 atmosphere to 1.03 atmosphere. What will the volume be at the surface? So when I look at this, we have 0.75 liters. Okay, now we have a distance, but Boyle's law didn't talk about anything with distance, so I'm going to ignore that for right now. And I have these two numbers here, which are pressure values. So because I'm looking at volume and pressure, this is an indicator that I'm going to use Boyle's law, which says P1V1 equals P2V2. Now when I go to plug my values in, this 0.75 liters is my initial value, or what I'm going to call my first value. Just like my pressure, or initial pressure, was 2.25, so this is going to be my 1. So when I plug in my numbers, I end up with 2.25 atmospheres times 0.75 liters, and that's going to equal my second pressure, which is 1.03 atmospheres, times my second volume, which I do not know. Now when I look at my equation, I have 3 known values, 1 unknown value, so all I have to do is multiply these two numbers by themselves, divide by the 1.03, and I end up with V2 is equal to 1.6 liters. And this is my final answer. The next law we're going to look at is called Charles's law. The best example that I can think of with Charles's law is, hopefully you've done this before at home, but if you take an inflated balloon and you stick it in the freezer, what you should have noticed happened is that that balloon actually deflated or decreased in size. Okay, and that's because there's a direct relationship between temperature and volume. Okay, so as our temperature increases, so does our volume, or vice versa. If the temperature decreases, the volume is going to decrease. Okay, and this is assuming that pressure does not change. Okay, and the kinetic molecular theory that you guys studied in chapter 12 should help explain this with the particle movement. Now, Charles was a French physicist, and he was the one that noticed that an increase in temperature caused an increase in volume, okay, when the amount of gas and the pressure were held at a constant. So those two things were not changing. So again, as a kinetic molecular theory stated, as a particle is heated up, volume will be affected. So if we look at this right here, we're given the equation V1 over T1 equals V2 over T2. And that's because our volume divided by our temperature should be the same as our post volume divided by our post temperature. Okay, and if we look at this mathematically on a graph, you can see that there's a direct relationship. And before we can use this equation or start applying things to it, like as in an example, we need to look at one more thing dealing with temperature. Most of the time, story problems will be given us the temperature in degrees Celsius, or if you're in a lab setting, you're going to be measuring things most likely in degrees Celsius. When we use these gas laws, the thing you have to remember about temperature is that we're not looking at the Celsius temperature, we're actually looking at the Kelvin temperature. And we talked about this earlier this year, but if you remember, some kind of key terms here that we talked about was an absolute zero. Remember, absolute zero is known as the zero on the Kelvin scale. This represents the lowest possible theoretical temperature, or in other words, it's when the atoms are at their lowest energy state. And if you recall, if you want to find your Kelvin temperature, you're going to take your Celsius temperature and add 273 to this. Okay, so now if we look at Charles's law again, the true definition says the volume of a given amount of gas is directly proportional to its Kelvin temperature at a constant pressure. So again, volume and temperature are changing here. Pressure is being held constant or is not changing. So let's go ahead and look at how this works in example 2. Example 2 says a helium balloon occupies 232 liters at 40 degrees Celsius. On a hot day, the temperature increases to 75 degrees Celsius. What is the new volume? So the first thing I notice is I have a volume and a temperature, and I have another temperature, and I'm looking for a volume. So because I'm looking for temperatures and volumes only, I know that I'm going to have to use Charles's law, which is V1 over T1 equals V2 over T2. And then, because I know that all temperatures have to be converted to Kelvin, I'm going to do that right from the very beginning. So these right here are going to be my first case, or my initial cases, while this one right here is going to be my second case. So T1 is going to be 40 degrees Celsius plus 273, which is going to give me 313 Kelvin. And T2 is going to be 75 degrees Celsius plus 273. And that's going to give me 348 Kelvin. So now that I've converted my temperatures, all I have to do is plug my numbers into the given equation. So my volume 1 was 232 liters divided by my 40 degrees Celsius, which is really 313 Kelvin. This is going to equal my volume 2, which I do not know, divided by the 348 Kelvin. Now you have 3 known values and 1 unknown value, so you can go ahead and solve this algebraically. And for those of you that don't remember how to do this, I'm going to multiply by 348 Kelvin over here to cancel those out, and I'm going to multiply by 348 Kelvin here. So, and this is really over 1. Your Kelvins are going to cancel, and that's going to give me a unit of liters, which is what I want. And if I go ahead and do the math here, what I end up with for an answer is that my second volume is equal to 258 liters. For the third and final law that we're going to look at today, his law came about because somebody took the initiative to sit there and contemplated what would happen if a balloon was rigid. Okay, meaning that it wouldn't expand or contract. What if volume was constant? Is there going to be a relationship between temperature and pressure, okay? And somebody took the time to research this, okay? And they did find that they were related, okay? Temperature is the direct result of collisions between gas particles and the walls of their container. And if you increase the temperature, you're going to increase the collision frequency of the particles, which is going to increase the energy. So theoretically, that should also increase the pressure if our volume or container size is not changing. So the scientist that came up with that was a guy named Gay-Lussac, okay? And he came up with his own law dealing with pressure and temperature. And we'll see that here on the next slide. So Gay-Lussac's law says that the pressure of a fixed amount of gas varies directly with the Kelvin temperature when the volume remains constant. So here we're holding our volume constant, and if you think about it, or if you look at the graph here, as my temperature increases, so does my pressure. So there's a direct relationship. Likewise, if your temperature starts to decrease, your pressure is also going to decrease. So this gives us the equation P1 over T1 equals P2 over T2. And we'll see how this formula is applied in our final example of the Part 1 video. Example 3 says the pressure of oxygen gas inside a canister is 5 atmospheres at 25 degrees Celsius. The canister is located high on Mount Everest. If the temperature decreases to -10 degrees Celsius, what is the new pressure? So again, I always start out every problem with what I'm given. Okay, I'm given a pressure and a temperature. So P1, T1, and I'm given, it looks like, a T2. So because I have pressure and temperatures, I know I'm going to have to use Gay-Lussac's law, which is P1 over T1 equals P2 over T2. And just like with Charles's law, we do have to convert our temperatures. So my 25 degrees Celsius plus 273 becomes 298 Kelvin. And my second temperature is going to be a -10 degrees Celsius plus 273 gives me a 263 Kelvin temp. So now when I plug in everything I know, I have 5 atmospheres over 298 Kelvin, and that should equal my pressure 2, which I do not know, divided by the second temperature, which is 263. So again, if I multiply both sides by 263 Kelvin, this tells me that my pressure 2 is going to be 4.41 atmospheres, and that would be my second pressure. Please let me know if you have any questions on this. We will do some homework assignments on this with the conclusion of the second video. Thanks and have a great day.